Hi, it's very nice to be here. Thank you very much to Michal and Piotr and all the other organisers for organising this really wonderful workshop. My slide up here says that I'm at University College London, but actually I only moved back from the US this time last week. And to be honest, I really didn't want to come to a conference the week after I moved continents. But when Michal invited me and I saw the list of people who were coming, then I couldn't say no. So, and I've really enjoyed it. So I'm going to be putting my Gilla hat back on and telling you about the work I've done for the last 3 years as a postdoc in the groups of Eric Cornell and Junyi, measuring the electron's electric dipole moment using trapped molecular ions. So our paper describing our most recent result came out a couple of months ago in Science and PRA, and we now have a measurement which sets the most stringent limits on the largest possible size of the Electron EDM. So I put some slides in here that I'm probably just going to skip because Mike already gave a nice introduction, as I hope he might. So I will jump just straight to the kind of principles of doing an EDM experiment, which I'll just kind of cover quickly because that's already been covered. But So the basic idea of doing an EDM experiment is you take your electron, which is, a ball of, everyone knows electrons are blue, and you put your electron in a magnetic field, and that splits the two spin projection states, right? So you have some energy difference between them. And in this kind of toy model of an electron EDM experiment, you can imagine measuring this energy difference by driving a transition between them using like an RF field or something like that. And then if we apply an electric field parallel to our magnetic field, and the electron has some non-zero EDM, then we'll see a small shift in that transition frequency, right? And if we reverse the direction of that electric field, then the sign of that shift will change. And if we compare those two frequencies, then we get a signal which is directly proportional to the size of the electron EDM, and of course the size of the electric field we apply. And so our technique is, exactly the same as what Mike said, where we want to have as larger electric field as possible to give us the highest sensitivity. And so we use molecules and we use molecular ions. So this is the team at Gilla who works on all things electron-electric dipole moment. The project is led by Eric Cornell and Junyi, and the main people who work in Generation 2 experiment I'm going to be talking about are me and the two PhD students, Tanya Rusi and Trevor Wright. So this is a schematic of our experiment. Every experiment starts with the creation of hafnium fluoride molecules, which is the molecules that we use at Gilla. So there's a stick of hafnium metal here, and we ablate the hafnium metal to create a hafnium plasma, and we do that in the presence of a supersonic expansion of argon gas with a tiny bit of SF6 in it. And so this hafnium plasma comes out and it reacts with the SF6 and it makes some hafnium monofluoride neutral molecules. And then they're entrained in this supersonic expansion of argon, and they fly down this differential pumping chamber, which is about 0.5 meter long, until they reach our ion trap chamber down there. In the ion trap chamber, then we ionize the molecules with two pulsed UV photons that come from two pulsed UV lasers, and then we trap them in our ion trap. So here's a picture of our ion trap. It's very different to most ion traps in the world in that it's really like a macroscopic object. This is like a thing kind of this size. It's kind of 20 centimeters tall and 10 centimeters across. That's like the trapping volume. And the cloud of ions we trap is like a centimeter-sized thing. To reiterate, I should probably have apologized at the beginning that these are, not ultra-cold molecules. I think the definition of ultra-cold sometimes gets stretched a bit, but I don't think anyone's definition of ultra-cold would apply to these molecules. These are kind of tens of Kelvin kind of temperatures. So the big advantage of using ions is that they're easy to trap, of course. So we've kind of heard about some of the problems of laser cooling these complex, heavy molecules which are sensitive to the electron EDM. And the big advantage of ions is that we don't need to worry about any of that. So we can trap these kind of tens of Kelvin molecules very easily, and that means we can have very long coherence times. So we have coherence times of a few seconds. The disadvantage compared to the typical beam experiments is that we have much lower count rates. We typically trap a few thousand molecules at a time. But we need to polarize the molecules, and so we have this kind of interesting, if I go back to this picture here, the ion trap is kind of interesting. It's got these 8 radial electrodes, and so we use the 8 radial electrodes to apply the normal kind of Poole trap voltages to confine the ions, but then we also apply oscillating voltages on the electrodes to apply a rotating electric field, which is larger than all the other electric fields experienced by the ions. But because they're ions, of course, you don't want to apply a static electric field, so we have this electric field rotating at about 375,000 times per second, and that keeps the ions confined whilst also polarized. So the ions just trace out these tiny circles in the trap of about half a millimeter radius. We do our experiments in the metastable triplet delta 1 state. I really enjoyed Typhus' talk yesterday, and I'm going to borrow his approach of graying out stuff I don't want you to be offended by. So the metastable, the triplet delta 1 state, of course, has orbital, we've got this molecule here, and we have one of the electrons has orbital angular momentum projected onto this internuclear axis of 2, and then we have 2 unpaired electrons giving us a spin of 1, and they combine to give us a total angular momentum projected onto this internuclear axis of 1. And that has this kind of magic properties that we have because the G factor for the spin angular momentum is double that of the orbital angular momentum. We get a very, very small G factor. They nearly cancel each other out. And the lambda doubling that comes from having a non-zero orbital angular momentum gives us these pairs of states of opposite parity, which are separated by really very small amounts. In hafnium fluoride, it's something like 740 kilohertz. So all molecules give you, much lower required electric fields in order to polarize the molecule. But these molecules with lambda doublets give you, much smaller. So we can fully polarize the molecule in fields of kind of a few volts per centimeter. So this is what the final state of the molecule looks like in an applied electric field. So from left to right, we've got MF, the total angular momentum of the molecule projected onto the electric field axis. And then we're just going to worry about these stretch states. So these 2 top states up here and these 2 bottom states down here. And you can think of these stretch states as being like these little illustrations. So these 2 states up here have their intermolecular axis aligned with or anti-aligned with the electric field, and these 2 states down here have their intermolecular axis aligned with the externally applied electric field. And then this effective electric field that the valence electron sees inside the molecule flips with this intermolecular axis. So these 2 states have their effective electric field pointing this way, and these 2 states have it pointing the other way. Meanwhile, then the unpaired electron spin points parallel to the externally applied field for these 2 states and parallel for these 2 states. And so now if we apply a magnetic field, then you can start to see that it looks a lot like the toy experiment I was talking about earlier. So we get these 2 states up here, which correspond to the electron being flipped in an electric field pointing this way, and these 2 states down here, the electron gets flipped in an electric field pointing this way. And if we compare those 2 energy differences, then we get a signal that's directly proportional to the Electron EDM. In actual fact, what we do is to perform the experiment twice, once with the magnetic field pointing one way and one with the magnetic field pointing the other way. And then we take some linear combination of these 4 energies that we measure, and that gives us a signal that's proportional to the Electron EDM and is sort of more resilient to systematic errors. So this is some example data. So these are kind of Ramsey fringes for the upper doublet. So measuring this state up here, or the energy difference between these 2 states up here and the energy difference between these 2 states down here is this blue fringe down here. And you can see that these Ramsey fringes go out to about 3 seconds in this case. And we're looking for an EDM shift, which is kind of tens of microhertz. And so that corresponds to kind of roughly one extra wiggle every 7 hours. And so in 3 seconds, we're looking for a difference of about 1/8,000th of a wiggle. Of course, this is all well and good, but the real kind of crux of any precision measurement experiment like this is the study of systematic errors. So really what I spent the last 3 years doing was mainly studying systematic errors. Any sort of self-respecting precision measurement experimentalist has to kind of get to grips with the idea that nature is out to get us, and we have to do our best to try and stop it. So the particular systematic error I obviously don't have time to talk about anywhere near all of them, but I just want to focus on one, which is there turns out to be a differential magnetic moment between the two doublets. And so to think about that, then I just want to show you the Stark shifts of the molecule. So this upper plot here, if you focus on that one to start with, this shows the Stark shift of the molecule in the kind of experimentally relevant field. So we're operating at about 60 volts per centimeter, so it's here. And so you can see our stretch states here, the two black states, one going up and one going down. They look extremely linear. But actually, if we zoom out a bit, or a lot actually, this is in kilovolts per centimeter rather than volts per centimeter, but it's the same plot. So this plot kind of fits in this tiny region down here. I've added these blue dashed lines to show what would happen if the Stark shifts were just linear for all fields. But you can see that they both start to curve down, and that's because we're now mixing in some of the next rotationally excited states. So the ground state is J equals 1, and then as you increase the electric field, you're always mixing in some of J equals 2. And so another way to think about that is, you know, we often write, and I already have done this today, and say that these molecules, these states have these molecules kind of fully aligned like this, but that's not quite true. Of course, to fully align a molecule, then you have to have some infinite superposition of rotational states. And so what's really happening is that we've got this kind of, you know, that the average alignment of the molecule with the externally applied electric field is about half. So we get a Stark shift of kind of half of the full dipole moment. And as we, in any kind of finite field, then actually what you have is that this upper state is slightly less aligned, and this lower state is slightly more aligned. So that's what gives you these, this Stark shift is getting steeper and steeper, and this Stark shift is getting shallower and shallower. And the magnetic dipole moment of the molecule, if you think the magnetic dipole moment comes from the motion of the electrons, and so the orbital motion of the electrons is of course tied to the internuclear axis because the electrons have to navigate their ray around the two nuclei. And then the spin of the molecules is tied to that orbital angular momentum. So the whole magnetic moment of the molecule is tied to the internuclear axis. It's very strongly coupled. And so when the molecule gets less aligned with the electric field, then so does the magnetic moment. And so we get this kind of differential change in the magnetic moment. And that looks kind of exactly like an EDM when you combine it with some kind of non-reversing magnetic field. And so the way we solve that is by doing, we measure this differential magnetic moment at our chosen electric field of about 60 volts per centimeter. It's a very small effect. It's about a part in 500 of the total magnetic moment, but this is very significant in the context of our measurement. And then we use the common mode frequencies, so we're measuring both the energies or the energy difference of both these doublets. And if we add them, if we look at the sort of mean of the two, that tells us the size of the non-reversing magnetic field. And then we can use the differential magnetic moment that we've measured to subtract the contribution from this effect. That works really well and works very nicely. The issue is that then there can be time varying effects. So if your electric field is varying in time, and particularly if it's varying in time in a way that's correlated with your externally applied magnetic field, then you can have some quite complicated effects that mean that this sort of cancellation procedure doesn't work anymore. So we spent actually a very long time kind of trying to characterize and reduce these effects in our experiment before we took our data set. Okay, I think I'm basically out of time, so I will skip to the conclusion, which is that we measured the Electron EDM to be less than 4 times 10 to the minus 30, which is an improvement by about a factor of 2 on the previous state of the art. And this 10 to the minus 30 centimeters is kind of a difficult thing to understand how small it is, but this is like saying that if you took the ratio of the size of an atom to the distance from Warsaw to London, that same ratio is multiplied by the classical radius of the electron. That's about 10 to the minus 30 centimeters. This is a really ludicrously small number. Yeah, so this is how the measurement fits in with the kind of the predictions of various beyond standard model theories. We're making some reasonable progress into this parameter space, but we're still well away from the standard model, so there's plenty of room for improvement for ultracold neutral molecule experiments, for example. We're probing mass scales for new particles which couple to the electron at single loop level at about 40 tera electron volts. And yeah, I guess that's about it. Thank you.
I think we can squeeze in one question. Anyone has a burning question? Burning question, over there.
So it's a very short question. I'm curious about your way to generate your ion beam. You use supersonic expansion, but in my understanding, normally it is a way to generate a quite fast molecular beam. Does it affect like the loading rate into your ion trap?
So yeah, you're right. It's a fast beam, but it's okay because we ionize them, and we can just apply voltages to stop from. I mean, you know, there's obviously a limit at some point, but it's very easy to stop the ions. You know, compared to these with neutral experiments where you have to kind of slow down the molecule with photons. We don't have that problem. Right? We can just apply some large voltage to the electrodes and stop the ions from kind of any velocity we like.
Thank you.
Any really last burning question? If not, let's thank the speakers again, all the speakers.